Hi, my name is Davi Tozoni and I'm a PhD student at New York University. I'll be presenting our work on a family of rhombic microstructures for irregular lattices. Advances in fabrication technologies made it possible to fabricate at a considerably low cost structures with complex geometry. This in turn makes it possible to create objects with predefined behavior using a single material by varying geometry. Microstructures play an important role in this. Consider the following scenario. Suppose we have a dictionary of microstructures with different values of Poisson's ratio nu and Young's modulus z. This is shown on the left. Now consider the bar on the right side where we know the expected material properties in each square cell, with Young's modulus varying in the horizontal direction and Poisson's ratio varying vertically. We can then use our pattern lookup dictionary on the left to place microstructures with corresponding elastic behavior in each position and then stitch all of them together to obtain our final shape. A fabricated example is shown in this slide. Here, a material distribution was obtained with an optimization procedure, allowing the object to flap its wings when squeezed. By placing the single material structures realizing these materials in each cell, we obtain the result shown on the right. Although interesting objects like the one just seen before can be built, the current approaches like Panetta et al. And Schumacher et al. Have some drawbacks. There is no guarantee of smoothness in the geometry dictionary between different material properties, as shown on the right. Because of that, we need a very large dictionary of cells for a dense sampling of the material space. It also leads to problems when tiling cells because of sharp changes in geometry. Finally, the input shapes need to be approximated by a subset of a regular grid, as also shown on the right. We then developed a family of microstructures with geometry varying smoothly as functions of material parameters. Smooth dependence on parameters makes it possible to represent the family as 8 splines. Our family supports non-square cells, which enables much better adaptation to complex domains without losing material property accuracy. Many details in our method are based on the idea of homogenization. In a nutshell, homogenization is a map from a periodic microstructure geometry to material properties. Imagine you have an infinite tiling of a microstructure. Seen from a far distance, you will see the materials homogeneous. Then, for a given point, we say that the homogenized elasticity tensor near this point maps the strain to stress of this homogeneous material. We refer to these stresses and strains as macroscopic. Because we use an infinite tiling and each cell behaves the same way, we can obtain these homogenized tensors by applying tension and shear test strains on single cells using periodic boundary conditions and computing the average deformation. In our case, in 2D, only 3 simulations are sufficient to obtain the tensor CH. Because we want to construct a table for looking up geometry based on desired effective material properties of a cell, we are interested in the inverse operation of homogenization. Given a material point, here described as a pair of numbers, Poisson's ratio and Young's modulus, we want to obtain its corresponding geometry using an inverse map. However, inverting homogenization is a difficult non-convex nonlinear PD constraint optimization. Despite this performance issue, some techniques apply the idea of per-point inverse homogenization like Panetta et al. And Schumacher et al. In addition to being very expensive, inverse homogenization presents another important issue. Its solutions are highly non-unique and they have a non-smooth geometry variation according to material properties. Notice in the example how for the same Poisson's ratio, geometries for Young's modulus equal to 0.018 and 0.022 are very different, even though the materials are very close. In this case, the shape in between obtained by interpolating geometry is likely to have very different properties and not the intermediate ones. Also, when tiling cells in an object, we can face interface errors and sometimes even disconnections. Another aspect that needs to be addressed to make the microstructure dictionary approach practical is cell shape. The easiest way to go is to use square cells only and trim these to the object's boundary. However, it doesn't adapt well to curved boundaries and very dense grids are needed to reduce the error in reproducing the desired material properties to an acceptable level. By zooming in, we can see how these cells are cut in this example. Notice how some of the microstructures are almost fully removed and others lose contact between each other with the trimming. During this procedure, these cells lose their original material properties. Observing the final deformation of the trimmed object, we see that it doesn't agree with the expected behavior, shown in the background in gray. Our contribution then is to solve some of the issues observed in these current techniques. We present a low-parametric microstructure family with smooth mapping. Notice how the microstructure geometry changes smoothly according to the Poisson's ratio and Young's modulus. Moreover, our framework is able to conform to arbitrary boundaries by approximating each quad to rhombic shapes, adding flexibility. We also guarantee tiling by using patterns with same topology in all cells and by smoothly changing the boundary node thickness when varying material. Observe how, in the example, a small change in Young's modulus leads to a smooth change in the shape. Our approach then relies on building a smooth map from material properties, Poisson's ratio nu and Young's modulus E, and shape of a rhombic cell, defined by angle alpha, to a geometry that fits that cell shape and has isotropic homogenized properties matching nu and E. Now we can start talking about our map design. Before explaining how our family is constructed, I first explain in more details how we parameterize the geometry of our cell structures. We assume that the cells can be approximated by a rhombus. We use diagonal symmetry, which means reflection symmetry on both diagonals and a constraint on the position of the connections to consecutive cells. This ensures that arbitrary rhombic meshes can be tiled easily. Also, it keeps enough degrees of freedom to obtain large range of elasticity properties. And, because of the axis of symmetry, we are guaranteed to have orthotropic materials, decreasing the dimension of the space of homogenized tensors. As parameters, we use a similar setup to Panetta et al. Work, with offsets for each node and thicknesses. The offsets corresponds to free barycentric coordinates of nodes in our symmetry-based cell, and thicknesses corresponds to the radii of the nodes. This is enough to also produce a large range of shapes. The bottom figure shows the graph representation of our pattern. Notice that we have 4 parameters for offsets and 4 for thicknesses, in a total of 8 parameters. Our objective is to obtain a map from isotropic properties nu and E to our geometric properties. In this figure, we represent the homogenization map that we want to invert, using an example with lower dimensions than our case. Here, we have our geometry space Bn with 3 parameters, P1, P2, and P3. The homogenization map H here maps B3 to an isotropic material space with 2 dimensions. In our case, remember that we have n equal to 8 and m equal to 4, since we have guaranteed orthotropy. Then, the idea is to reduce space Bn to an m-dimensional space V, obtaining an m to m homogenization map H', which is the restriction of H to V and is at least locally invertible. In summary, we need to reduce the set of parameters to an m-dimensional set V and obtain the inverse of H' on the isotropic subspace. As a first step, we can run a coarse and full parameter sweep with our geometric parameters. We use around 5 values per parameter for a total of 540,000 tuples of values. For each tuple, we inflate the pattern, generating a mesh. Then we run a homogenization and obtain our orthotropic elasticity tensor. And finally, we can filter the results close to isotropy, obtaining the range shown on the plot. We refer to the part of the material space for which we have a geometric structure as coverage of a family. The sweep provides us with a rough approximation of it. We then start our parameter reduction, since we are interested in obtaining an m-to-m dimension mapping, in our case 4D to 4D, which makes it possible to extract an inverse mapping for homogenization. Overall, we are looking at a linear subspace of the geometric parameter space, for which the coverage is almost the same as for the whole space. PCA can be used for this. Instead, we found it useful to eliminate some dimensions first. We analyze slices with fixed values of parameters. Then we identify values for which the isotropic material coverage remains close to the original one, with all initial n equal to 8 parameters. And we then fix these values, reducing the dimension of our parameter space. In our case, we reduce it from 8 to 6D by fixing position of an internal node, and then from 6 to 5D by fixing the thickness of the boundary node. Notice how the coverage is still similar to the original one with 8 parameters. We then complete our parameter reduction by using PCA to identify new parameters that combine the original and dependent ones, in order to reduce dimensionality. We filter out tuples of geometric parameters that are not close to isotropy. Then, we run PCA to identify the most important parameters and their combinations. In our case, we were able to identify with PCA a linear relationship between thickness and coordinate of a node, reducing our parameter space to 4D, while keeping a good coverage as seen in yellow in the chart. Notice that this last reduction also doesn't compromise much of our coverage. Now, we have a 4D to 4D map from a subspace of geometric parameters to 4D space of material properties, but we want the inverse mapping. To achieve that, we use the following algorithm. Consider a fourth grid of values in the geometry subspace, here illustrated as a red 2D grid. For each hypercube G in the geometric parameter side, we obtain the mapped 4D hypercube M on the material space. Then, we partition each hypercube in each of the spaces into simplices. For a point PM with nu and E in material space, we can find a simplex Tm on material space that contains PM by checking barycentric coordinates. Then, we obtain Pg by applying the same coordinates in the corresponding simplex of the geometry space. But notice that this operation is relatively slow, and it's not viable to do this every time we need to compute the parameters for a given material. So, we pre-compute the data and interpolate it. By defining a grid on material space and running this exact algorithm for all points, we can obtain the corresponding set of target geometric parameters. We observe that the data for every geometric parameter is very smooth and can be approximated by a spline with relatively few control points. This way, the map can be stored in a compact form, a set of 8 2D spline patches for a fixed rhombus angle. The previous algorithm is able to produce an initial coverage in orange in the plot using only our reduced set of 4 parameters. We then expand it using optimization while maintaining smoothness. For each neighbor of our current coverage, we minimize an energy composed by an elasticity tensor fitting term, penalizing distance to the target material properties, and regularization terms, trying to keep solution close to the initial one. Here, our initial solution is obtained through extrapolation using the smooth map P obtained for the initial coverage, which increases smoothness. Now, having a map for square cells, the objective is to extend it to general rhombic shapes. But first, let's discuss why we are using rhombic cells in the first place. The first reason is related to the fact that not all shapes can be used for periodic tiling and running homogenization. Because of its congruent sides and parallel opposite sides, any rhombus fits that purpose. In addition, as said before, accepting only rectangular cell shapes makes it difficult to conform to arbitrary boundaries. Approximating cells to rhombic achieves a better result at that. Finally, a rhombus can be defined by a single angle alpha. This makes it easier and less expensive to run sweeps and optimization procedures when exploring the material space. On the downside, it's impossible to use precisely rhombic cells for an arbitrary shape, so in some cases a small number of quads of the meshes we use deviate from rhombic substantially, but overall the cells can be optimized to be close. Having our coverage for square cells, we can expand to lower values of the angle. For each point in our 90 degrees coverage, we start an iterative procedure running optimization for lower and lower values of angle alpha, always using the solution from the previous angle as a start for the new optimization. We do this from 90 to 45 degrees, obtaining the result shown in the plot on the right. Notice how we have a very smooth change of the parameters. When running the same expansion for all initial points, we obtain the following coverage. Having data for all angles, we can produce our final mapping P from material to geometry. And we do this by feeding splines to the values of each geometric parameter. Given as input Poisson's ratio, Young's modulus, and angle alpha, our map P provides the 8 parameters necessary to produce the corresponding microstructure's geometry. Now that we have our map, we can analyze it to see how it fits our objectives. Here you can see how the geometry changes for various combinations of Young's modulus and Poisson's ratio. Note that small changes of parameters result in small changes in geometry. Our change in geometry is also smooth in the rhombus angles alpha direction, as seen in our chart and also visually in our structures. We can also analyze our map for specific rhombic shapes. See the case of alpha equal to 45 degrees shown on the right. Despite the shorter range of material properties achieved for this angle, we still have a smooth set of data that can be interpolated. This makes it possible to use our map also in rhombic shapes, and allow us to have quad meshes that conform to arbitrary boundaries. Finally, having a smooth map P helps us with tileability. Our choice of cell shape and symmetry and the fact that we use the same pattern and topology for all cells already guarantee that our structures connect when we tile them. But having a smooth map helps even more, since the connection region also varies smoothly according to material properties. Now, compare with the result from inverse homogenization on the right side. With our method, our structures tile almost perfectly when slowly varying Young's modulus, which is not the case for the structures obtained with inverse homogenization. Here's a comparison of our domain, shown in orange, with the one obtained using inverse homogenization, shown in blue. Notice that we have almost the same coverage. We only seem to lose a bit of values on the right, for large values of Poisson's ratio, but this seems small, considering that smoothness is a big restriction. Also, notice how we can test the coverage with a much finer grid, since we have a direct map being able to interpolate results, which is not possible when using inverse homogenization. As we use only few samples in spline interpolation, we consider the error computing the distance between target properties and homogenization on the geometry generated with MapP. Here we have the errors for both Poisson's ratio on the left and Young's modulus on the right. The general error is in the order of 10 to minus 2 to Poisson ratio and 10 to minus 3 for Young's modulus. Let's see now how we can use our map in some practical applications. After constructing the map, our parametric family can be used in the context of a two-scale optimization pipeline. First, we run a quad mesh optimization in our original mesh, approximating each cell to a rhombic shape. Then, with our new mesh, we run material optimization, which optimizes material distribution according to boundary conditions set by the user. Here, we use a local global technique described in Panetta et al. Work. Finally, we use our smooth mapping in a pattern matching procedure, assigning geometry according to the material properties of each cell, using our MapP. Then we can project each of the geometries to their original quad shapes to form the final geometry. Using this pipeline, we produce the pliers shown on the right. On the left, we have the result obtained using a similar pipeline with inverse homogenization. The gray background shows the expected behavior. First, notice how our geometry is visually smoother than the one produced with inverse homogenization. When zooming in, we can see more clearly that the error is lower when using our technique. In this project, we also produced some of our examples using a laser cutter. Here, we present pliers made of blue acrylic. Notice how we can hold small objects like this SD card, for example. Another example that we produced, this time with foam, was this bar that transforms into a sphenoidal shape when squeezed. We also use foam to produce a sad ghost, and, as expected, a happy ghost. As a conclusion, we were able to design a smooth and compact map from isotropic material properties to geometry, with proven accuracy. We also implemented a complete framework that can produce an optimized object for a given set of boundary conditions from any quad mesh. As future work, it should be possible to achieve a larger range of material properties by using different topologies and different techniques for expanding coverage. Moreover, we could explore a pipeline to produce orthotropic materials as well, since this work we focus on isotropic materials in order to have results that are more mesh independent. During experiments, we observed that collisions and nonlinearity can largely affect behavior for objects when dealing with large displacements. An idea would be to use more sophisticated simulations to improve our results. And finally, a future project would be to try solving the same problem in 3D. And we already have a prototype for it. Using the pattern shown in the figure in the bottom, we use the same steps for obtaining a reduced set of geometric parameters and obtain a map from material properties to 3D geometries in a cube. Thank you very much.